As it happens, the actor Timothée Chalamet was the first to go on top of the sphere and promote his latest movie, Marty Supreme. But when he got there, look what he found: an observatory, the Galileo Project Observatory, on top of the sphere next to Timothée Chalamet. The reason for that is that 6 months earlier, I was there with members of the Galileo Project research team to install this observatory and look for anomalous objects in the sky. And so the images taken of Timothy standing on top of the sphere, which became a huge ping pong ball to promote his movie, also promote the Galileo Project. The goal of the Galileo Project is to search for extraterrestrial outliers, namely objects that move outside the performance envelope of human-made technologies like the familiar airplanes, satellites, balloons, or drones. A key component of the Galileo Project observatories in Massachusetts, Pennsylvania, and Nevada is a triangulation system of multiple units that enable measurements of distance, velocity, and acceleration of anomalous sources out of the few million objects that are being monitored every year in the sky. To separate these outliers, we use state-of-the-art machine learning software. In recent months, the Galileo Project, under my leadership, hired 4 new postdocs whose main task will be to analyze the new data harvested by the Galileo Project observatories. As a result, the coming months will be exciting if we discover outliers. I told my research team that they should have no hesitation in calling my phone in the middle of the night if they detect an unambiguous anomalous phenomenon. There is nothing more exciting than finding an extraterrestrial package in our mailbox. Once the Galileo Project research team finds it, we can attempt to figure out its content as well as the intent of its sender. Hopefully, the extraterrestrial package will include a love message, like the box of fine chocolates that I received from my wife recently for Valentine's Day. And now to a scientific piece of news. On January 30th, 2026, at 10:25:37 UTC, a bright green fireball from a meteor was spotted over Wellington Harbour in New Zealand. The meteor was moving at an amazing speed of 71 kilometers per second relative to Earth. By itself, this speed is very close to the maximum value possible for the impact of an object bound to the solar system with Earth. The upper limit on the impact speed of solar system meteors follows from the following simple reasoning. The Earth orbits the Sun at a speed of 29.8 kilometers per second. This follows from balancing the centrifugal acceleration v squared over r with the Sun's gravitational acceleration gm over r squared, where r is the radius of the Earth's orbit, g is Newton's constant, and m is the mass of the Sun. The result is v squared equals gm over r. On the other hand, the speed required to escape from the Sun's gravitational potential at the radius r is obtained by balancing the kinetic energy per unit mass, 0.5 VE squared, with the potential energy, gm over r. This gives an escape speed that's larger than the Earth's speed, v, by a factor of the square root of 2, yielding VE equals 1.414 times V equals 42.1 kilometers per second. The largest speed of a solar system meteor relative to Earth is obtained for an Oort cloud bolide, which happens to collide with Earth head-on, opposite to the motion of Earth around the Sun. The upper limit on the relative speed of a solar system meteor is therefore 29.8 plus 42.1 equals 71.9 kilometers per second. This is very close to the speed of the recently discovered meteor. Hence, This meteor could have originated from the solar system if it collided with Earth head-on, opposite to its motion around the Sun. If not, then its high relative speed would imply that it is interstellar in origin. What do we know about interstellar meteors? In June 2023, I led an expedition to the Pacific Ocean aiming to retrieve materials from the first recognized interstellar meteor, IM-1. This meteor was detected on January 8, 2014 at 17:05:33 UTC. Its velocity relative to Earth was only 45 kilometers per second, but it arrived from behind the motion of the Earth around the Sun. Correcting for the Earth's motion implied a speed of 60 kilometers per second relative to the Sun, well above the escape threshold of VE equals 42.1 kilometers per second for solar system objects. Indeed, the US Space Command confirmed the interstellar origin of IM-1 at the 99.999% confidence level. The IM-1 impact site was localized based on the light radiated from the IM-1's fireball, which was detected by sensors aboard US government satellites. The light curve of the fireball showed 3 successive detonations, separated by a tenth of a second from each other, with the last flare being the brightest and at a ram pressure of 200 megapascals. This stress is 4 times higher than the maximum ram pressure up to which the toughest iron meteorites from the solar system survive. Indeed, IM-1 displayed the highest material strength among all meteors in the CNEOS Fireball catalog of NASA JPL. The expedition recovered sub-millimeter scale spherules, molten droplets, with a chemical composition that is different from known solar system materials. Upon entering the solar system, IM-1 moved with an interstellar velocity of about 60 kilometers per second relative to the local standard of rest of the Milky Way galaxy, similar to that of 3I Atlas. The ocean expedition was documented in a Netflix documentary and a new book to be released within the coming year. Is the 2026 January 30th meteor of interstellar origin as well? To find out, I used the velocity components, latitude, longitude, and altitude data compiled by the CNEOS Fireball database and corrected for the Earth's motion in collaboration with my postdoc, Richard Cloet, to find out that the velocity of this meteor relative to the Sun was only 42.4 kilometers per second, very close to the escape threshold of 42.1 kilometers per second. The difference between the two is within the measurement uncertainties. Since the local abundance of solar system objects is a few orders of magnitude larger than that of interstellar objects, this meteor most likely originated in the solar system. The 2026 meteor over New Zealand collided with Earth nearly head-on and probably originated in the outer solar system, in difference from IM-1, which exploded at an altitude of 18.7 kilometers over the Pacific Ocean. This new meteor exploded at a much higher altitude of 89.0 kilometers, implying a much lower material strength since the Earth's atmosphere is highly rarefied at this altitude. This inference is consistent with the expected properties of a fragile iceberg from the Oort cloud, which could disintegrate at a low ram pressure. Both fireballs radiated similar amounts of energy of about 3.82 times 10 to the power of 10 joules, suggesting bolides with a radii of order 0.4 to 0.5 meters. Here's hoping that in the coming years, we will witness the crash of an interstellar object that shows the characteristics of a Voyager-like probe from an extraterrestrial technological civilization that launched it from another star a few billion years ago. After all, Most stars formed billions of years before the Sun, and our own Voyager spacecraft will reach the opposite side of the Milky Way galaxy within that time difference. The search for interstellar meteors continues.